So the graph to the left gives the velocity of a car as it travels away from home along a straight road. All right, so A asks you to describe the velocity of the car. Who can tell me about that velocity of the car? Yes, I think that's a 40 because this is 20. It does look like a 10 because the line cut it off, but yes. So the velocity of the car is a constant 40 feet per second. Great. All right, question. How far does the car travel during the first 5 seconds of its journey? $200 feet. How'd you get it? Just 5 times 40 is all you got to do, right? Because you got 5 seconds. I'm going to throw some units in here just to show you how the units work out on this. Times 40 feet per second, right? If you think about your units, the seconds cancels with the seconds. That gives you 200 feet. Now, you don't have to do that problem with the units in it, but just to show you how it works out there. Okay, so I want us to think about what we just did there. We had 5 seconds here. We multiplied it by the 40 right there. So this was 5, this was 40. What did we essentially find? The area of that rectangle, right? Okay, that's going to be important. Okay? All right, so C, it is known that at t equals 0 seconds, the car was 400 feet away from home. How far is the car away from home when t equals 8 seconds? Okay, how'd you get it?
Just do like 8 seconds, 8 times 40 plus 400.
Okay, so 8 times 40 is going to give us 320. That's how far, that's the feet that the car traveled. We need to add it. It was already 400 feet away from home, so we need to add to that, right? So 400 plus 320 is going to give us 720 feet from home. Since our velocity is positive, then that distance should be increasing, right? If we had a negative velocity, if this is like below the x-axis, then we would need to subtract for that. So, but since our velocity is positive, it would be further away. Good question. I'm pretty sure that this particular question is not going to be on there. However, this exact question with a more complicated graph might be on there. But just the flat line 40 feet per second graph, that's not going to be on there. Yeah. Yeah. Okay. So, all right, let's make it a little more difficult. Okay. The graph to the left shows the velocity of a car carrying a crash dummy. So it's going to ask us, what is the velocity of the car at t equals 3 seconds? Okay, right here is where we're looking. 3 seconds is right here at that point. It's just 16 feet per second. Okay, what is the acceleration of the car for the time period shown on the graph? How would we find that? What's that? Okay, so it's a derivative, which is the slope, right? So we just need to find the slope of this line. So like if we You can pick a couple points wherever, if I think it's 3, because this would be, that's at 7. We go up 1, 2, 3, over 1. Be careful on your scale here, because all those little tiny boxes are not what you're looking at. That should be right, I think. Or if you can also do points. That's the point 0, 7, and this is the point 3, 16. So if you want, you can do 16 minus 7 over 3 minus 0 to get 9 over 3, which gives us 3 what units? Nope. Feet per second per second. Some of you on your penguin problem put penguins per penguin per month or day or whatever it was. What would it mean to have a penguin per penguin? Yeah, I'm not sure what it would mean, but it would be a weird situation, right? So that one was, I think it was months, penguin per month, or days, whatever the time was. Or it could have been penguin per month squared for that. You also can write it this way. It is okay to write this as feet per second squared. The reason that I hesitate to do that is because of the wrong answer that Luke just gave me of feet squared per second, because feet squared, penguin per month might kind of like jump out at you as, oh wait, that doesn't quite make sense. But feet squared per second, like you can have feet squared per second. That's a possibility. You would be talking about the area of something if you're talking about that. So that's one reason I kind of prefer feet per second. Okay? All right. Okay, next part of this question. How far does this car travel in the first 7 seconds? So, this is a more difficult question than the one we just saw, right? Because in the first problem, we had a constant velocity, right? So we just had to take that velocity and multiply it by our time. And that gave us our distance that was traveled. In this case, our velocity is not constant. At 0 seconds, we're going 7 feet per second, then 10 feet per second, then 13 feet per second. You're accelerating. You're going faster and faster. So this is not as easy to do. What do you think?
Is it like, so you have like 10 over, like 10, 1 second. Would you like, is it like something just like cubed? It's like cubed because it's multiplied by 3?
If I do velocity divided by time, that would give me acceleration. Because velocity feet per second divided by seconds would be feet per second times 1 over seconds, which would give me feet per second squared. So if I divided velocity by time, it would give me acceleration, which is not, it's like the wrong direction of what this is asking for. So, no, but good thing to consider. What do you think? Okay, so on that last one, I pointed out we were doing 5 times 40, right? And that basically gave us the area, right? Because if we take velocity times time, right? If we do feet per second and we multiply it by seconds, right? Which would be like seconds over 1. Seconds cancel. We just get the amount of feet that we've traveled, right? So to find the answer to this, it's not exactly going to be a triangle, because is this shape right here a triangle? No. But we do want to find the area of this shape right here. So you got a couple options on how you can find that. You can break that into a rectangle and a triangle. Or you can do area of a trapezoid, because that is a trapezoid with these vertical sides are parallel. Either one is going to work fine. If we want to do a trapezoid, this side right here is 7. This side right here is what, 28? And then this side right here is 7. What's the formula for area of a trapezoid? What? That. Yep. Okay, base 1 plus base 2 times height divided by 2. Or 1/2 base 1 plus base 2 times height, whichever way you want to think about it. So this is your area of a trapezoid. You're going to see that we haven't found a need for knowing this formula in a while, probably, but because of several things we're going to do, we're going to need to know trapezoid formula here soon. So, so we would have 7 plus 28 times 7 divided by 2, and that is going to be, oh gosh, 35 times 7 divided by 2, and 35 times 7, 245 divided by 2, we're going to get 122.5. 122.5 what? No, that's the correct decimal. What are my units? Feet. Right, so. The bases have to be parallel to each other. So, usually when we think of a trapezoid, we think of this, right? And this is a base, and this is a base. That's like base 1, base 2 for that. But the sides, for a trapezoid, the sides that are your bases have to be the parallel sides. So in this case, that has to be your 7 and your 28, because this side and this side are not parallel to each other. Plus, we couldn't find the length of this side without having to do a bunch of work anyway. So now, maybe you're saying, Ms. Hyatt, that sounds awful. I don't want to do that. Here's, you've got this option, and it might be easier, particularly if you don't know trapezoid formula. 7 times 7, that's 49. Do 1/2 times 7 times, let's see, that's going to be, now be careful because the height of this wouldn't be 28. It would be 21. 21, find that, and then add them together. That's an option. Although there is something coming up where we're going to need to know the area of the trapezoid. It's something you're going to need on your exam, so we need to know it anyway for that. So this is kind of cool because we can figure out how far this will travel, even though its velocity is not constant, right? Because up until this point, you have not been able to do something like that for that. So we can find the distance traveled for that. Okay, let's look at another one. The graph to the right shows the rate at which the amount of water in a tank changes after t minutes. So, A, at what rate is the amount of water in the tank changing at t equals 3? Okay, it would just be 6, because this is the rate that we're looking at. You would have 6 gallons per minute. Okay, what about at 6? Wait, hold on. At what rate is the amount of water in the tank changing at t equals 6? Do we have a problem here? I said uh-oh. Do we have a problem? If we were trying to talk about the rate of the rate, we would have a problem. But this graph we're looking at is the rate, and it's just going to be 8. Right? So this can kind of be confusing sometimes because you're already looking at the rate graph. You're just reading these off. Right, so you're just looking at the y coordinate that goes with this. Now, if they had asked you at what rate is the amount of water in the, or at what rate is the rate of the amount of water changing, the rate of the rate, which is kind of like acceleration, although we can't use that word acceleration here because acceleration is just for motion, then we would need to do a derivative and we could not do that because of the sharp term. But this is just asking us to read the point off, okay? C, does the amount of water in the tank ever decrease? Yes or no? This definitely decreases. What is this? This is the rate. So Jeremy said no, it never decreases, and Troy said it just slows down, right? Because how do we know that our amount of water in the tank is still increasing here? That rate is above the x-axis. It is positive. So, no. The rate is positive. So, the amount increases. So, as Troy said, it slows down, but it's still increasing, right? This tank is filling up. It fills up, faster and faster at first, then at a constant rate for a couple minutes, and then at a slower rate, but still filling up, right? Right. Right. Like my kids were watching YouTube videos where people were like having like a water challenge where you gotta like get a cup and you gotta try to like fill it up. You take turns. It was actually kind of fun. And you gotta like just put like a drop in, and the person who makes it overflow is the loser. It was kind of fun actually.
Beer game. Like if you lose, you like.
Probably, it sounds like probably it's a drinking game, but we were using water at our house. All right. Is the rate of change of the amount of water in the tank increasing or decreasing at t equals 5 minutes? Okay. Let's think about what it's asking. So we just said the amount of water in the tank always increases, right? Is this asking us about the amount of water in the tank? What is it asking us about? The rate of change of the amount of water in the tank. Okay? At 5, which is right here, we would say neither, right? So, yeah, I know. I will say probably on an AP problem, they would probably throw or neither in there. Because this time, while our rate of change is positive, it is neither increasing nor decreasing. So it's asking about whether this graph is increasing or decreasing. It's constant at t equals 5. All right, how much water is added to the tank over the first 10 minutes? What have we got to do to find how much water? This is asking about amount of water. We're going to find the area of the thingy, because if we take gallons per minute and multiply it by the number of minutes, which is what the x-axis is calculated with, we'll get gallons, which will be what we want, right? We want to know the number of gallons. So we got a weird shape here. This one you're definitely going to want to split into rectangles and triangles. No. because you got 5 sides. 1, 2, 3, 4, 5. So you could split it, like to split it into the least amount. Well, no, I would do this. I'd split it like this. That's how I would do it. There's other ways to do it, whatever you prefer. So for this part, you're doing a triangle. So 1/2 times 4 times 8. So that's going to be 16 for that piece. This part is just 2 times 8. So also 16 for that piece. And then for this, you can do a trapezoid for this one. This one is a trapezoid. Or you can make it a rectangle and a triangle if you want. 1/2 times, let's see, 8 and 5 for your bases. And then your height would be 1, 2, 3, 4. So that's going to be like 2 times 13. I think we'll get 26 for that. And so if we add all of those together, 16 plus 16 plus 26, it's going to be 32 plus 26, which will give me 58. Does that sound right? For that, and I should put gallons with that, 58 gallons.
Wait, so what's the area of the triangle?
1/2 base times height.
I split that.
Into a triangle and a rectangle. Yeah, that'll be fine. You can do that for sure.
I don't know.
Yeah. We have to learn trapezoid soon, but you can get away with not knowing it yet.
Why do we have to learn?
1/2 base times height.
If you can just break all
It's just a half of a rectangle, right? Because all rectangles could be cut in half, right? Rectangle would be base times height, right?
Yeah, and you just put
And you just cut it in half because it's half. A triangle is half of a rectangle.
That's crazy.
So what's the trapezoid?
A trapezoid actually, like if you think of the formula, it's 1/2.
A rectangle.
Let's do 1/2 B1 plus B2 times the height. What you're really doing for the area of a trapezoid, I find this interesting, is a trapezoid, usually we think of it looking kind of like this, right? And this is your B1 and your B2. What you're doing here, this part right here, you could think of it as half of a hexagon, but the hexagon formula is more complicated than that. And it has to be like a regular for that.
You just do it for you just do that, and then is that a
What does this find when you do 1/2 times B1 plus B2? What? If I add two numbers together and divide by 2, what is that? It's the average. This is your average of your bases times the height. So what this is essentially doing is it's like finding the point that's like halfway between B1 and B2. Actually, no, I've drawn that wrong. Like, it is taking the length halfway between B1 and B2, and it is like making this a rectangle. It's like taking, this piece right here fills up over here, and then this little piece right here, I haven't drawn it perfectly, fills up over here, and it makes it a rectangle. So the average of the bases is like your base, and then you're multiplying by that height there. So it's kind of cool. Yeah. Yeah, shapes are cool. I used to love teaching geometry. Geometry was destroyed by Math 1, 2, and 3. And I'm still angry about it because they chopped it into all little pieces and they sprinkled a little bit in every class. And it's like you touch on it for just a few days and then you never like put it all together. And geometry, in my opinion, is probably the most useful high school math that we teach because any carpentry needs a little bit of geometry. And it is technically still in those classes, but chopping it into pieces to me just like makes it worse. But they didn't ask me. So. Maybe. I'm not the geopolitical history of Africa is not something I'm qualified to speak on. So I'll let you study that one, Liam. All right.
Like the idea of splitting it up, I think that's
Okay. All right. Let's look at this. All right. A drag car travels down track. Selected speeds of the drag car are given in the table below. I want to know the average acceleration of the car for the 2.5 seconds shown on the table. What should I do to find average acceleration? Okay, it is the slope between
2 and 140 and 2.5.
Say it again.
2 and 140.
That would estimate your acceleration at 2.25.
Yeah.
We want to know average acceleration for over the 2.5 seconds shown on the table. We'll use 0, 0, and 2.5, 145. This is an average rate of change. This is the slope between the endpoints of that range. So, if we're using the point 0, 0 and 2.5, 145, we would just have 145 minus 0 over 2.5 minus 0. I realize those are kind of not necessary. 145 divided by 2.5 is going to be 58. So 58, what are my units?
The feet per second squared.
Feet per second squared or feet per second per second. If you're having trouble with units, just think about what you just did. You subtracted the y's. They were feet per second, right? And then you subtracted the x's. They were measured in seconds. So you could include them in the problem, right? Feet per second on top, per second on the bottom, feet per second squared. Okay, that is your average acceleration for the car. All right, now, if I want to estimate the acceleration of the car at 0.75, what would I do here?
0.5 and 60 and 1.
Yes, we're going to use, this time we're going to use these 2 points. Right here, the points closest to that actual value. And so we'll say 110 minus 60 over 1 minus 0.5. And we will get 50 over 0.5, which will be 100 feet per second. All right, now here's where it gets more difficult. Oh, yes, thank you. Feet per second squared, thank you. Okay, so A is finding an average. It's the slope between the endpoints of your range. B is an estimation of your instantaneous rate of change, right? So you're using the 2 points closest to that value. But the way that you do them is pretty much the same except for the points you choose. All right, so, but A and B, that stuff is review, right? That is derivative stuff. That stuff is review. But what we're talking about new here is C, estimate the distance that the car traveled in the 2.5 seconds. Oh, we don't even have a line right here, right? Let's have a table. Let's graph these points. I put this graph here for a reason. Maybe that'll help us, right? We got 0, 0. We got 0.5, 60. We got 110, 1.5, 130, 2, 140, 2.5, 145. So, just based on what I know about a car accelerating, I would assume that this is probably going to be a smooth curve, right? Unless you got a crazy driver. I guess if you got somebody that's really bad on gear changes or something, you might have some jerky things happening here. But if this is an automatic transmission here, you should have a relatively smooth curve right there. Yeah, how are we going to have it? Fun. I don't think that's a circle. Now, it did say estimate, right? So it wants us to guess. Are we going to be able to get the exact answer on this? We're not. Okay. So, like, are you talking about, like, maybe this?
Yeah.
Okay, that'll work. There's a triangle. Then maybe do, like this and like that. Or we could just make that a trapezoid if we wanted. And then... maybe something like this.
You could have like one big triangle there.
Yeah. It's a guess, for sure. What? It's definitely not going to be as good as what I've drawn here in red, right? So if I did one big triangle, that would be this right here, which would be an estimate that you could use, right? It just says estimate, and it didn't say how. So that would be an estimate that would have some logic behind it that you could use, but pretty much all of this area right here would be lost on that. So it'd be way lower than it should be if we did just that big triangle right there. For that. For the sake of time, because I got something else I want to do, I'm not going to actually figure this out right now because it's going to take you a while to calculate all that. But right now we're just kind of exploring what we should do. You would need to make some shapes there and try to figure out the area of those shapes underneath. It would not be correct. It would not be the exact value because even if I did like what I have in red here, it's pretty close. But you can kind of see like you got this little sliver right here that you're missing, and this little sliver right here that you're missing if you do that. So I'm, for the sake of time, and because I want to get to the next problem, and I've got an activity we're going to do, I'm not going to figure that out. But you could do a square, and then you'd have to add like rectangle, like other little rectangles and triangles around it. You could do that, but. You mean kind of like do something like maybe, take, this is another option. You could take like this piece right here and try to get it to match that piece. I don't think I've got it right there. But you could kind of like turn it into a rectangle where this piece fills in the extra over here. That would work. That would work too. Any of these are going to be, at this point, good options for us to try because it just says estimate, right? And we're not going to actually do them for the sake of time. Now, this question right here is a crazy question because this question this is a piece of history for us right here. And every year, whenever I get to this question, I wrote this question probably about February 4th of 2020. This is the time of year whenever Coach Wood is walking by my room and sticks his head in and says, "Hey, Miss Hyatt, how many Coronas do you have to drink to end up with coronavirus?" This is happening right here. And so I was like, this was in the news just a little bit. This coronavirus, it's in China, was in the news just a little bit. And I went and looked up these death rates to make a problem out of it in 2020 while we were still in school in February. This was right before spring break that we never came back from, right? So here's a piece of history right here, written as a math problem. Because I was writing this, I can remember myself telling the class things like, hopefully it's going to stay over there in China. We won't have to worry about it. Telling them things like, it's not It's not like it's 60% fatal. You know, it's it's like it's not good, but it's got a lower fatality rate. Saying these things, totally not knowing anything about the future, that it was going to totally shut us down and change lots of things. Yeah, that really went up. That really increased there. That increased a lot. So this is a little piece of history for you here. So from January 23rd to January 29th, the number of daily deaths increased at a rate of. What would we do for that? Yeah, and let's go ahead and do this because we need. Let's make this 0 right here. So we make this 0, 26. So 0. That'll be 3, and then this will be 6. This will be 7. Then we got January 31st, February 1st, February 2nd. That'll be 10, and then 12. So we need to change those to days instead of dates. Otherwise, we can't analyze the data. Okay? So from January 23rd, which is our 0, right, to the 29th, which is 6, I would need to, I'm looking at the rate at which this increased. So I would do 38 minus 8 over 6 minus 0. So 30 over 6, which will give us 5. What are the units on that? Deaths per day, or deaths per day squared. That almost doesn't sound like it's a rate of a rate because it's asking just about the rate that the daily deaths increased, but daily deaths is a rate because that is measured in deaths per day. So this is a deaths per day per day. So what you're kind of seeing is like at this point, every day there's 5 more deaths per day than there were the next, because this is not just number of deaths, this is deaths per day. All right, what about from January 30th to January 4th? We do same thing, different points, right? So we do 43 minus 66. I don't know why I did that one first. Over 7 minus 12. I don't know why I put that in that order to get negatives on top and bottom, but I did. So what is that? Negative 23 over negative 5. And we get 4.6. And again, that's deaths per day. Okay? So, at this point, I would say things like, oh, well, it is increasing, but look, our rate of change is not increasing as fast as it was. Or so I thought at the time. All right. So then it says to estimate the total number of deaths due to the coronavirus between January 23rd and February 4th. So if we look at the graph here, at 0 we had 8. At 3 we had 24, which would be like right here. At 6, we've got 38. I'm estimating here. 7, we've got 43. 10 is 58. 10, 58. 8 and 12, 66. So if I look at this, this is not a perfectly straight line, but it said estimate, right? And to estimate, to me, that is close enough to a pretty straight line that I think I can just do the area of that trapezoid right there. So the height right here is 8. The height right here is 66. And those bases are 8 and 66, and the height is 12. So we would have 1/2 times 12 times 8 plus 66. So that is 6 times 74, which is 444. And what would that be measured in? Depths. Because when we do area, we're taking deaths per day and multiplying it by deaths, or by days. So that would just give me the number of deaths. So here on somewhere around February 4th, it had to be after February 4th because I was making this problem using data that existed. So 444 people. And I was like, don't worry about it, guys. It'll be fine. It's not going to get that bad. And it did. Okay.
I really have to eat that soon.